Today we shall continue our study of the simple harmonic oscillator. We shall find the wave function and energy of the nth excited state of the simple harmonic oscillator and some relevant things. As we have discussed in the previous lecture that if we have the ground state wave function and ground state energy, and if we operate psi naught by the A plus operator, then we shall get the wave function of the first excited state. If you want to make an equal sign, then you have to put a constant A1 say, and this is A plus and psi naught, where A1 is a constant and the energy of the first excited state of the simple harmonic oscillator will be E naught plus h cut omega. But we know E naught is half h cut omega, which can be written as 1 plus half h cut omega. So this is the energy of the first excited state, and this is the wave function of the first excited state. Similarly, if we operate this one again by A plus operator, then we get this, and this is A plus square psi naught, and this one will give you the second excited state, which is psi 2. And if you may want to equate with A plus square psi naught, then you have to put a constant. Let us suppose this is A2 and this A plus square psi naught. And energy of the excited state, the second excited state, is E2, which will be E naught plus 2 h cut omega, and this is half h cut omega, 2 h cut omega. So if you take common, h cut omega will have this. So this is E2. So this is the energy of the second excited state, and this is the wave function of the second excited state. Similar to this, and if we continue doing this, then we can write down the wave function of the nth excited state, and which can be written as a constant an, then a plus to the power n psi naught, and en we can write down is e naught plus n into h cut omega, which is half h cut omega and n h cut omega. We take common h cut omega, then n plus 1 half h cut omega. So we see that our wave function and energy of the nth excited state of the simple harmonic oscillator in the nth excited state of the simple harmonic oscillator in the nth excited state, then we will have this. Okay, now our task is to find this constant an. Okay, in doing this, we recall that our Hamiltonian operator is this, and another expression of the Hamiltonian operator of the simple harmonic oscillator is this. Now, if we write down the Schrödinger equation for the nth excited state of the simple harmonic oscillator, now if we substitute this one here, then we'll have an En we just found out, and this is this. Okay, from this equation we can write down okay, so is if we cancel this, then n psi n. So you see that the product a plus and a minus is an operator, and you see this is an eigenvalue equation. And the eigenvalue is a number. Therefore, we can say that a plus a minus is a number operator. Okay, similar to this, if we write down the Schrödinger equation for the nth excited state, but instead of this one, if we use this one, then you could also show that a minus a plus psi n is equal to n plus 1 psi n. So you see a minus a plus is also a number operator. Here the eigenvalue of this number operator a minus a plus is n plus 1. Now from now on we will have these two formulas, and these two formulas we can apply to find this this constant. Okay, another theorem that we are not going to prove this theorem, just we should mention only those theorems. And the theorem is, if you have a plus operator here and psi m and here psi n, this is the inner product, and this is equal to psi m, and here this one will become a minus operator psi m. Similarly, if you have psi a minus operator here, and you will have a plus operator here. We are not going to prove this. Okay, from now on we shall use this as the granted theorem. Okay, now we are ready to find the constant an for the wave function of the nth excited state of the simple harmonic oscillator. Let a plus psi n equal to cn psi n plus 1, and therefore we have the inner product so a plus psi n, so you can write down here cn psi n plus 1 and cn psi n plus 1, but this is the inner product, so we can write down like this. The integration of this the limits of this integration from minus infinity to plus infinity, and this is the from normalization. If we assume that psi n plus 1 is normalized, then this integral is 1 total probability, so we have cn square here. Suppose this is 1, assuming is normalized. We also have so if we bring this operator a plus here, and this is the number operator. We know this is n plus 1 psi n. Inner product, definition of inner product. So we can bring n plus 1 outside the integral sign, and here modulus square of psi n. Again, this is 1 if we consider psi n is normalized, so this is n plus 1. Okay, if we say this is 2, then now you see 1, the left hand side of 1 and the left hand side of 2 are same. So equating 1 and 2, we get Cn modulus square is equal to n plus 1. But you see n plus 1, n is a real number, integer, so Cn is real, therefore Cn is square root of n plus 1. Now if we put this value of Cn in this equation, then we can write down, therefore this is Cn, so is square root of n plus 1 psi n plus 1. From this, psi n plus 1 can be written as 1 divided by square root of n plus 1, and here a plus psi n. Okay, in this relation, if we substitute n is equal to 0, 1, 2, say j, then when n equal to 0, we have psi 1 equal to 1 divided by square root of 0 plus 1 a plus, and this is psi naught, which can be written as 1 divided by square root of 1 a plus psi naught, which can be written as this. Okay, when n is equal to 1, then we will have here psi 2. So this, now to substitute this psi 1 from here, then we'll have, and this is we can write down this like this. And if you continue doing this, okay, let us suppose again take n equal to 2, then we'll have say n plus 1, so psi 3 and 1 divided by square root of 2 plus 1 a plus, and this is psi 2. Now you put this psi 2 from this, so 1 by square root of 3 a plus, and this one is 1 divided by square root of factorial 2 a plus to the power 2 psi naught, which can be written as 1 divided by square root of factorial 3 a plus to the power 3 psi naught. So if you do this way, then we can write down psi j equal to 1 divided by square root of factorial j a plus to the power j psi naught, or psi n is 1 equal to divided by square root of factorial n a plus to the power n psi naught. So you see, comparing this with psi n is a n a plus to the power n psi naught, we get a n constant is 1 divided by square root of factorial n. Therefore, we have found out the constant an. Therefore, we get the wave function and the energy of the nth excited state of the simple harmonic oscillator. Okay, now we have a theorem. This is the last topic of today's lecture. Wave functions psi m and psi n are orthogonal to each other for m is not equal to n. Okay, we shall prove this. We have, if you consider a minus psi m and a minus psi n, and if we bring this a minus here, then it will become a plus. We know from a previous theorem. So is psi m and this one we know the n psi n, and this is this. If we actually applied the definition of inner product, on the other hand, we also have now we bring this a minus from here to here, so it will become a plus a minus psi m and this is m psi m psi n, and if we apply again the definition in terms of integration of inner product, then you can show that this we suppose that this is equation 2. Now you see the left hand sides of these equations 1 and 2 are same, therefore equating one and 2, we get this. So we can bring this one on the left hand side of the equation. But now if we apply our given condition that if m is not equal to n, then then this one must be 0. Showing that psi m and psi n are orthogonal to each other. Okay, so this is the end of today's lecture. In the next lecture, we shall consider some other one-dimensional problems. For example, a particle trapped in a one-dimensional infinite potential well, and one-dimensional single-step barrier.